In the vast dark expanses of our universe, where light years stretch into the unfathomable, lies one of the most powerful phenomena known to science: neutron stars. These celestial objects, remnants of massive stars that have undergone cataclysmic supernova explosions, are both beautiful and terrifying in their might. They are the universe's ultimate paradox: incredibly dense yet diminutive remnants of death, yet sources of unimaginable energy. But how exactly did they come to be, and what is the horrifying power that these stars hold? The birth of neutron stars. Neutron stars are among the most fascinating and powerful objects in the universe. Their story begins with the life cycle of massive stars, those many times larger than our Sun. When these giants come to the end of their life, they go out with a bang, a spectacular explosion known as a supernova. This dramatic event is the birthplace of neutron stars, marking the transformation of a dying star into something extraordinary and bizarre. A massive star spends millions of years burning nuclear fuel in its core, producing energy that counteracts the force of gravity pulling inward. This delicate balance keeps the star stable for most of its life. However, when the fuel runs out, the balance tips. Without the outward pressure from nuclear fusion, gravity takes over, causing the star's core to collapse. The outer layers of the star are then blasted into space in a supernova explosion, one of the most energetic events in the universe. As the core of the star collapses, it undergoes a phenomenal transformation. The immense gravitational force crushes the core's atoms, causing protons and electrons to combine into neutrons. The result is a dense ball of neutrons, a neutron star. Despite having a mass up to twice that of our Sun, a neutron star is incredibly small, typically only about 20 kilometers in diameter. To put this in perspective, it's as if you squeezed the mass of a mountain into a space the size of a city. This collapse creates an object of staggering density. A single teaspoon of neutron star material would weigh billions of tons on Earth. The gravity on a neutron star's surface is also mind-bogglingly strong, about 1 billion times stronger than Earth's gravity. This means that if you could stand on a neutron star, which you can't, as you'd be instantly crushed, you would weigh 1 billion times more than you do on Earth. The existence of neutron stars was first proposed in the 1930s by Swiss astronomer Fritz Zwicky and German-American astronomer Walter Baade. Working at the California Institute of Technology, they suggested that supernovae could result in the formation of stars composed mostly of neutrons. This was a bold and groundbreaking idea at the time, as the concept of such dense objects was difficult to grasp. Zwicky and Baade's pioneering work laid the foundation for future research and observations that would eventually confirm the existence of neutron stars. Studying neutron stars poses a significant challenge due to their small size and great distance from Earth. However, advances in technology have enabled astronomers to observe and learn more about these enigmatic objects. Modern observations rely on a variety of techniques and telescopes, each providing unique insights into the nature of neutron stars. One of the most important tools for studying neutron stars is the X-ray telescope. Neutron stars are often detected by the intense X-rays they emit, particularly if they are part of a binary system. In such systems, the neutron star can pull matter from its companion star, heating it up to extreme temperatures and causing it to emit X-rays. The Chandra X-ray Observatory and the XMM Newton telescope are among the leading instruments used to observe these high-energy phenomena. Another crucial technique involves radio telescopes, which are used to detect pulsars, a type of neutron star that emits regular pulses of radio waves. Pulsars are like cosmic lighthouses, with their magnetic poles emitting beams of radiation that sweep across the sky as the star rotates. The regularity of these pulses allows astronomers to study the rotation and other properties of neutron stars in great detail. The Arecibo Observatory, until its collapse in 2020, and the Parkes Observatory in Australia have been instrumental in pulsar research. In recent years, gravitational wave detectors such as LIGO and Virgo have opened up a new frontier in neutron star studies. When two neutron stars collide, they create ripples in the fabric of spacetime, known as gravitational waves. These collisions are not only spectacular cosmic events, but also provide invaluable information about the properties of neutron stars. The detection of gravitational waves from a neutron-star merger in 2017 marked a milestone in astronomy, allowing scientists to observe the event in both gravitational waves and electromagnetic radiation. The anatomy of a neutron star. A neutron star is a cosmic marvel composed of different layers, each with its own unique properties. At its heart lies the core, the densest part of the star. Surrounding the core is the crust, which, despite being less dense, is still incredibly compact compared to anything we know on Earth. Above the crust is a thin atmosphere, a wispy layer that interacts with the surrounding space. The core of a neutron star is where things get truly extraordinary. It is composed almost entirely of neutrons, subatomic particles that are found in the nucleus of atoms. Under the immense pressure of gravity, these neutrons are packed together in a way that defies our everyday understanding of matter. The density is so extreme that a single cubic centimeter of neutron star core would weigh hundreds of millions of tons on Earth. Surrounding this core is the crust, which is also incredibly dense, though not as much as the core. The crust is made of ions and electrons, but as you move deeper, the density increases, and the atoms are stripped down to their neutrons. This layer is just a few kilometers thick, but it plays a crucial role in the star's structure and behavior. It's in this crust that we find the neutron star's magnetic field, one of the most intense in the universe, capable of reaching a strength 1 trillion times greater than Earth's magnetic field. Above the crust lies the atmosphere, a thin layer only a few centimeters thick. This atmosphere is composed mainly of hydrogen and helium, and it's here that the star interacts with its surroundings. The atmosphere can be incredibly hot, reaching millions of degrees, and it emits X-rays and other forms of radiation that we can detect with our telescopes. The forces that keep a neutron star from collapsing under its own gravity are fascinating and come from the realm of quantum mechanics. One of the key principles at work is neutron degeneracy pressure. In normal stars, the pressure from nuclear fusion reactions prevents collapse, but in neutron stars, the story is different. Here, quantum mechanics comes into play. The Pauli exclusion principle, a fundamental concept in quantum physics, states that no two neutrons can occupy the same state in the same space. This principle creates a pressure that counteracts gravity, known as neutron degeneracy pressure. It's this pressure that supports the star and prevents it from collapsing further into a black hole. Neutron stars are incredibly dense, with gravity so strong that if you were to drop something from a height of 1 meter, it would hit the surface in a fraction of a millisecond at over 1,000 kilometers per second. To put the density into perspective, imagine a sugar cube-sized piece of neutron star material. This tiny piece would weigh about 1 billion tons, which is roughly the same as the weight of all the humans on Earth combined. Comparing the gravity on a neutron star to that on Earth is almost impossible to grasp. On Earth, if you jump, you come back down gently. On a neutron star, the gravity is so intense that you would be crushed almost instantly. Even light struggles to escape the pull of a neutron star, which is why they can bend light around them, an effect known as gravitational lensing. The extreme conditions inside a neutron star also create a unique environment where nuclear reactions and quantum effects occur on a scale and intensity not seen anywhere else. The core of a neutron star is so dense that the neutrons are packed together almost touching. This state of matter, called neutronium, is incredibly rare and can only exist under the most extreme conditions. The outer crust of the neutron star is also fascinating. It consists of a lattice of atomic nuclei immersed in a sea of electrons. As you move inward, the density increases and the nuclei are packed closer together until they dissolve into a soup of neutrons and protons. This inner crust is a place where strange and exotic forms of matter can exist, including free neutrons and superfluid components. One of the most intriguing aspects of neutron stars is their magnetic fields. Neutron stars can have magnetic fields 1 trillion times stronger than Earth's. These magnetic fields affect everything from the star's atmosphere to the space around it. In some cases, the magnetic field is so strong that it can affect the structure of atoms, stretching them into thin, elongated shapes. This intense magnetic field also accelerates particles to nearly the speed of light, creating beams of radiation that we see as pulsars. Pulsars are a special type of neutron star that emit regular pulses of radiation. This happens because the neutron star is spinning rapidly, and its magnetic poles emit beams of radiation that sweep across the sky like a lighthouse. When these beams point towards Earth, we detect a pulse. Pulsars are incredibly precise, with some rotating hundreds of times per second. They serve as cosmic clocks, allowing astronomers to measure time with incredible accuracy. The magnetic monsters. Neutron stars are already extraordinary, but some take things to another level with their magnetic fields. These neutron stars, known as magnetars, have the most powerful magnetic fields in the universe. Their magnetic fields are 1,000 times stronger than those of typical neutron stars, reaching up to 1,000,000,000 times the strength of Earth's magnetic field. Magnetars are true magnetic monsters. The intense magnetic fields affect every aspect of their existence. These fields are so strong that they can alter the structure of atoms, stretching them into thin, elongated shapes. The magnetic pressure is so great that it can crack the crust of the magnetar, leading to starquakes, which are similar to earthquakes but far more powerful. These starquakes can release massive amounts of energy in the form of gamma rays. One of the most spectacular and terrifying events associated with magnetars are magnetar storms. These storms occur when the magnetic field lines snap and reconfigure, releasing a huge burst of energy. The result is a gamma-ray burst, one of the most energetic explosions in the universe. These bursts can be observed from Earth and provide critical insights into the nature of magnetars. The first observed magnetar storm occurred on March 5, 1979. Two Soviet spacecraft detected a powerful burst of gamma rays from a distant source. This event, now known as the March 5 event, was later determined to originate from a magnetar in the Large Magellanic Cloud, a nearby galaxy. The burst was so intense that it temporarily blinded the detectors on the spacecraft. Since then, many more magnetar storms have been observed, each providing more information about these incredible objects. One of the most famous magnetar storms happened on December 27, 2004. A magnetar located about 50,000 light-years from Earth in the constellation Sagittarius released a burst of gamma rays that was so powerful it affected Earth's atmosphere. The burst was detected by numerous satellites and observatories around the world. This event highlighted the incredible energy output of magnetar storms and their potential to impact Earth even from vast distances. While these gamma-ray bursts are fascinating to study, they also pose potential hazards. If a magnetar were to flare close to Earth, the effects could be devastating. The intense gamma rays could strip away the ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. This could lead to a significant increase in skin cancer and other health problems for living organisms. The magnetic fields themselves could disrupt satellites, communication systems, and power grids, leading to widespread technological failures. Fortunately, magnetars are relatively rare, and none are currently close enough to pose an immediate threat to Earth. However, studying these magnetic monsters helps scientists understand the potential risks and develop strategies to mitigate them. By observing magnetar storms and analyzing their effects, researchers can gain valuable insights into how these events could impact our planet. Despite the potential dangers, magnetars are also objects of immense scientific interest. They provide a unique laboratory for studying physics under extreme conditions. The intense magnetic fields and high-energy environments around magnetars offer insights into the behavior of matter and the fundamental forces that govern the universe. By studying magnetars, scientists can test theories of physics and explore new frontiers in our understanding of the cosmos. Magnetars also have a role in the broader picture of the universe. They are connected to other astrophysical phenomena, such as supernovae and gamma-ray bursts. By understanding magnetars, scientists can learn more about the life cycles of stars, the dynamics of supernova explosions, and the mechanisms behind gamma-ray bursts. These connections make magnetars an essential piece of the puzzle in our quest to understand the universe. The energy dynamics of neutron stars. Neutron stars are among the most energetic objects in the universe. Their energy dynamics are complex and awe-inspiring. They emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. This radiation is a key aspect of their nature and reveals much about their internal processes and environments. The radiation output of neutron stars is immense. Compared to other cosmic phenomena, neutron stars are incredibly bright, especially when observed in X-rays and gamma rays. For instance, a single neutron star can outshine an entire galaxy in X-rays. This high radiation output is due to the extreme conditions on and around the star. The intense magnetic fields, rapid rotation, and high temperatures all contribute to the energetic emissions. When comparing neutron stars to other cosmic phenomena, it's clear they are powerhouses of radiation. While a typical star like our Sun emits most of its energy in the form of visible light, neutron stars primarily emit in the high-energy part of the spectrum. This difference in radiation output highlights the unique physical processes occurring within neutron stars. The luminosity of a neutron star, which is the total amount of energy it emits per second, is closely linked to its energy sources. One significant source of energy for neutron stars is their rapid rotation. Neutron stars can rotate hundreds of times per second, and this rotation generates a tremendous amount of energy. As the neutron star spins, its intense magnetic field accelerates charged particles to nearly the speed of light, producing beams of radiation. These beams can be observed as pulsars, where the rotation causes the beams to sweep across our line of sight, creating regular pulses of radio waves or other radiation. Another vital energy source is the residual heat from the neutron star's formation. When a neutron star is born from the collapse of a massive star's core, it is extremely hot. Over time, this heat radiates away, but the process can take millions of years. This thermal emission is primarily in the form of X-rays, which can be detected by space-based telescopes. The heat output from a neutron star can provide insights into its age and thermal history. Young neutron stars are typically hotter and emit more X-rays, while older ones are cooler and emit less. The thermal emissions from neutron stars have significant implications for our understanding of their structure and behavior. By studying the heat output, scientists can infer details about the neutron star's crust and core. For example, the cooling rate of a neutron star depends on the properties of the superfluid in its core and the heat conductivity of its crust. Observations of thermal emissions help refine models of neutron star interiors and provide clues about the exotic states of matter that exist under such extreme conditions. Neutron stars also have another intriguing aspect of their energy dynamics, their magnetic fields. As mentioned earlier, the magnetic fields of neutron stars are among the strongest in the universe. These fields can interact with the neutron star's surroundings, creating magnetospheres filled with charged particles. The interactions between the magnetic field and these particles generate additional radiation, contributing to the neutron star's overall energy output. The study of these magnetospheres is crucial for understanding the full picture of neutron star energy dynamics. The intense energy emissions from neutron stars can also impact their surroundings. For instance, a neutron star in a binary system can accrete matter from its companion star. As this matter falls onto the neutron star, it is heated to extreme temperatures, producing X-rays. This accretion process is another significant source of energy for neutron stars and can lead to phenomena such as X-ray binaries and millisecond pulsars. Understanding the energy generation processes in neutron stars is key to unlocking many astrophysical mysteries. These processes are governed by the principles of quantum mechanics and relativity, providing a natural laboratory for testing fundamental theories of physics. The extreme conditions in neutron stars push these theories to their limits, offering unique insights that cannot be obtained from any other object in the universe. Gravity's extreme playground. Neutron stars offer a glimpse into gravity's extreme playground, where the fabric of space-time itself is twisted and warped in ways that push the boundaries of our understanding. One of the most remarkable aspects of these celestial objects is their role in the production of gravitational waves, ripples in space-time that were predicted by Albert Einstein's theory of general relativity. Gravitational waves are produced by some of the most violent and energetic processes in the universe. One such process is the collision of neutron stars. When two neutron stars orbit each other, they gradually lose energy through the emission of gravitational waves, causing them to spiral closer together until they eventually collide. These collisions release an immense amount of energy, sending powerful ripples through the fabric of space-time. The first direct detection of gravitational waves from a neutron star collision was made in August 2017 by the LIGO and Virgo observatories. This event, known as GW 170817, was a landmark discovery in astrophysics. Not only did it confirm the existence of gravitational waves, but it also provided a new way to observe the universe. The collision of the two neutron stars was also detected in various forms of electromagnetic radiation, including gamma rays, X-rays, and visible light. This simultaneous observation across different wavelengths marked the beginning of multi-messenger astronomy, allowing scientists to study the same cosmic event through multiple channels. The detection of GW 170817 provided valuable insights into the nature of neutron stars and the extreme conditions in which they exist. The gravitational waves from the collision carried information about the masses and the radii of the neutron stars, offering clues about the properties of the dense matter within them. The electromagnetic observations revealed the aftermath of the collision, including the formation of heavy elements like gold and platinum, which are produced in the intense environment of a neutron star merger. The immense gravitational fields near neutron stars cause space-time to warp dramatically. This warping is an essential aspect of Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Near a neutron star, this curvature is extreme, and the effects can be observed in several ways. For instance, light passing close to a neutron star is bent by its gravity, an effect known as gravitational lensing. This bending can make the neutron star appear distorted or magnified when viewed from Earth. Another consequence of the extreme gravity near neutron stars is time dilation. According to general relativity, time runs more slowly in stronger gravitational fields. This means that if you were close to a neutron star, time would pass more slowly for you compared to someone farther away. This effect, while predicted by Einstein, is not something we experience in our daily lives, but it becomes significant in the vicinity of massive objects like neutron stars. Neutron stars also provide a natural laboratory for testing Einstein's predictions about the behavior of matter and energy under extreme conditions. The precise timing of pulsars, a type of rotating neutron star, allows scientists to test the effects of general relativity with high precision. For example, the double pulsar system, where two neutron stars orbit each other, has provided some of the most stringent tests of general relativity to date. Observations of this system have confirmed several predictions of the theory, including the emission of gravitational waves and the resulting orbital decay. The study of neutron stars and their gravitational effects has deepened our understanding of general relativity and its implications for the universe. By observing these objects, scientists have been able to confirm many of Einstein's predictions and explore the limits of his theory. The extreme conditions near neutron stars push the boundaries of our knowledge, offering insights into the nature of gravity and the fundamental laws of physics. Exotic states of matter. The study of neutron stars opens a window into some of the most exotic states of matter in the universe. The extreme conditions within these stars lead to the formation of matter unlike anything found on Earth. From the dense core to the outer crust, neutron stars are a showcase of unique and bizarre states of matter that challenge our understanding of physics. Deep within the core of a neutron star, where pressures and densities are at their peak, scientists theorize the existence of a state of matter known as quark-gluon plasma. Under normal conditions, Protons and neutrons are made up of quarks, which are held together by particles called gluons. However, the extreme conditions in the core of a neutron star may break down these protons and neutrons into their constituent quarks and gluons, creating a soup-like mixture. This quark-gluon plasma is thought to resemble the conditions that existed just moments after the Big Bang, providing a glimpse into the early universe. The idea of quark-gluon plasma is supported by theoretical physics and experiments conducted with particle accelerators, such as the Large Hadron Collider. These experiments recreate the high-energy conditions necessary to form quark-gluon plasma on a very small scale. The study of neutron stars offers the opportunity to observe this state of matter on a much larger scale, providing valuable insights into the behavior of matter under extreme conditions. Another fascinating hypothesis related to neutron stars is the existence of strange matter. Strange matter is composed of strange quarks, which are heavier than the up and down quarks that make up ordinary matter. In the core of a neutron star, the pressure may be sufficient to convert some of the quarks into strange quarks, resulting in a new, stable form of matter. This strange matter could potentially be even denser than the already incredibly dense neutronium that makes up the core of a neutron star. The idea of strange matter is intriguing because it suggests the possibility of entire stars made of this exotic material, known as strange stars. While no direct evidence for strange matter has been found yet, the study of neutron stars provides a promising avenue for exploring this hypothesis. If strange matter does exist, it could have profound implications for our understanding of the fundamental forces and particles that make up the universe. Moving outward from the core to the crust of a neutron star, we encounter another bizarre state of matter known as nuclear pasta. The crust of a neutron star is subject to immense gravitational forces that compress the nuclei of atoms into unusual shapes and structures. This leads to the formation of matter with textures resembling various types of pasta, such as lasagna, spaghetti, and gnocchi. These shapes are formed as the nuclei arrange themselves into layers, tubes, and other complex configurations to minimize energy in the extremely dense environment. Nuclear pasta is not just a curious name. It represents a unique phase of matter that challenges our understanding of nuclear physics. The study of nuclear pasta can provide insights into how matter behaves under extreme pressure and density, conditions that are not easily replicated on Earth. The unusual properties of nuclear pasta, such as its high strength and the way it conducts heat and electricity, have implications for the thermal and magnetic properties of neutron stars. The existence of nuclear pasta was first predicted by theoretical models, and recent computer simulations have provided more detailed insights into its structure and behavior. Observations of neutron stars, particularly through their thermal emissions and magnetic fields, can help confirm the presence of nuclear pasta and improve our understanding of its properties. Neutron stars versus black holes. Neutron stars and black holes are both extraordinary outcomes of stellar evolution, representing different endpoints for massive stars. These objects, though born from similar processes, exhibit distinct characteristics and behaviors that make them fascinating subjects of study in astrophysics. Neutron stars and black holes form from the remnants of massive stars that have exhausted their nuclear fuel. When a star much more massive than our Sun runs out of fuel, it can no longer support itself against the force of gravity. The core collapses under its own weight, leading to a supernova explosion. For stars with a mass up to about 20 times that of the Sun, this collapse results in the formation of a neutron star. If the original star is even more massive, the core continues to collapse into an even denser state, forming a black hole. The formation of neutron stars involves the compression of protons and electrons into neutrons, creating an incredibly dense object. Black holes, on the other hand, form when the gravitational collapse continues unabated, compressing matter to a point of infinite density known as a singularity. The region around the singularity, from which not even light can escape, is called the event horizon. This marks a fundamental difference between neutron stars and black holes. While neutron stars remain as tangible, albeit incredibly dense objects, black holes represent a point where normal physics breaks down and space-time is infinitely curved. The gravity of neutron stars and black holes is extreme but operates differently. Neutron stars have a surface, albeit a highly compressed one, with gravity billions of times stronger than Earth's. This means that an object dropped from a height of 1 meter would hit the surface at about 2,000 kilometers per second. Despite this, it is theoretically possible to escape a neutron star's gravity given enough energy. In contrast, black holes have such a strong gravitational pull that nothing can escape from within their event horizon, not even light. The escape velocity at the event horizon exceeds the speed of light, making black holes essentially invisible and detectable only by their interactions with surrounding matter. The immense gravity warps space-time to such an extent that time itself behaves differently near a black hole, an effect predicted by Einstein's theory of general relativity. Observing and differentiating between neutron stars and black holes relies on understanding their unique signatures. Neutron stars, particularly pulsars, are detected by their regular pulses of radiation. These pulses are produced by the rotation of the neutron star, sweeping beams of radiation across the sky. X-ray telescopes can detect the high-energy emissions from neutron stars, especially those in binary systems where the neutron star accretes matter from a companion star, heating it to extreme temperatures and emitting X-rays. Black holes, by their nature, cannot be observed directly. Instead, they are detected by their gravitational influence on nearby objects and their effects on surrounding matter. In a binary system, a black hole can pull material from a companion star, forming an accretion disk. The friction and compression of this material as it spirals into the black hole generate intense X-rays, which can be detected by space telescopes. Additionally, black holes can be identified by the motion of stars orbiting an invisible mass, as seen in the center of our galaxy with the supermassive black hole known as Sagittarius A*. Gravitational waves also provide a powerful tool for studying both neutron stars and black holes. The collision of neutron stars or black holes generates ripples in spacetime that can be detected by observatories like LIGO and Virgo. The first detection of gravitational waves from a neutron star merger in 2017 confirmed many predictions about these objects and opened a new era in astrophysics. Similarly, the detection of gravitational waves from black hole mergers has provided insights into their properties and the nature of gravity itself. The study of neutron stars versus black holes helps scientists understand the extremes of physics and the life cycle of stars. Both objects challenge our understanding of matter, energy, and the fundamental forces that govern the universe. Neutron stars, with their dense cores and magnetic fields, offer a glimpse into the behavior of matter at nuclear densities. Black holes, with their event horizons and singularities, push the boundaries of our knowledge about gravity and space-time. A cosmic light show. Neutron stars put on a spectacular cosmic light show, emitting radiation across the electromagnetic spectrum, from radio waves to gamma rays. Among these emissions, X-rays hold particular importance. Observations made by powerful X-ray telescopes like Chandra and XMM Newton have provided valuable insights into the nature and behavior of neutron stars, revealing their secrets in vivid detail. The Chandra X-ray Observatory, launched by NASA in 1999, is one of the most sophisticated X-ray telescopes ever built. It has a unique ability to detect and image X-rays from high-energy regions of the universe, such as the remnants of exploded stars and regions around neutron stars. Chandra's sharp vision has allowed astronomers to study the detailed structure of neutron stars and their environments, providing clues about their formation and evolution. XMM Newton, a European Space Agency mission, complements Chandra with its own set of powerful X-ray instruments. Since its launch in 1999, XMM Newton has provided extensive data on neutron stars, helping scientists understand the intense and dynamic processes at play. Together, these telescopes have revolutionized our understanding of neutron stars, revealing the complexity and beauty of these objects. X-ray emissions from neutron stars are incredibly diverse. In isolated neutron stars, X-rays often come from the hot surface, heated by the residual heat from the star's formation or by magnetic and rotational processes. In binary systems, Where a neutron star accretes matter from a companion star, the infalling material is heated to millions of degrees, producing bright X-rays. These emissions provide a wealth of information about the physical conditions and processes occurring in and around neutron stars. One of the key techniques used to study neutron stars is spectroscopy, the analysis of light emitted by these objects. By examining the spectrum of X-rays and other radiation from a neutron star, astronomers can infer its composition, temperature, density, and magnetic field strength. Neutron star spectroscopy involves breaking down the light into its component wavelengths and identifying the unique fingerprints of different elements and ions. Spectroscopy has revealed that neutron stars have atmospheres composed mainly of hydrogen and helium, with traces of heavier elements. The spectral lines observed in X-rays can provide precise measurements of the surface temperature and gravitational redshift, allowing scientists to probe the star's intense gravitational field. These observations help build a detailed picture of the neutron star's surface and its underlying structure. Neutron star mergers, where two neutron stars collide and merge, are among the most energetic and dramatic events in the universe. These collisions produce a phenomenon known as a kilonova, a transient astronomical event that shines brightly across the electromagnetic spectrum. Kilonovae are caused by the radioactive decay of heavy elements produced during the merger, releasing an immense amount of energy and light. The visual spectacle of a kilonova is a rare and awe-inspiring event. When two neutron stars spiral into each other and collide, they create a burst of gravitational waves, followed by a flash of gamma rays. As the ejected material from the collision expands and cools, it emits light across the spectrum, from ultraviolet to infrared. This light show can last for days to weeks, gradually fading as the radioactive material decays. The kilonova observed following the GW 170817 event in 2017 was the first of its kind to be detected. The gravitational waves from this neutron star merger were picked up by LIGO and Virgo, and within hours, telescopes around the world were trained on the source. The resulting observations provided a detailed look at the kilonova, revealing the production of heavy elements like gold and platinum. This discovery confirmed that neutron star mergers are a primary source of these elements in the universe. Kilonovae not only provide a visual spectacle, but also offer valuable scientific data. By studying the light curves and spectra of kilonovae, astronomers can learn about the physics of neutron star mergers, the properties of the ejected material, and the processes that produce heavy elements. These events also help refine models of neutron star interiors and the behavior of matter under extreme conditions. Neutron stars in supernovae. Neutron stars are not just the fascinating remnants of massive stars, but also key players in the dramatic events known as supernovae. These stellar explosions are among the most energetic phenomena in the universe, and the formation of a neutron star is intrinsically linked to the dynamics of these powerful blasts. When a massive star exhausts its nuclear fuel, it can no longer support itself against the pull of gravity. This leads to a catastrophic collapse of the star's core, followed by a rebound that sends shock waves outward, causing the star's outer layers to explode in a supernova. During this process, the core of the star is compressed to extreme densities, resulting in the formation of a neutron star. The presence of a neutron star in the core plays a crucial role in the mechanics of the supernova explosion. The intense gravitational collapse and subsequent formation of a neutron star release an enormous amount of energy. This energy drives the supernova explosion, propelling the outer layers of the star into space at incredible speeds. The shock waves generated by this explosion spread out, heating the surrounding interstellar medium and triggering the formation of new stars. This process injects heavy elements produced during the star's life and in the explosion itself into the galaxy, enriching it with the building blocks for future generations of stars and planets. The remnants of these supernova explosions, which include both the expanding shell of gas and the newly formed neutron star, have significant impacts on their environments. The shock waves from the explosion compress nearby clouds of gas and dust, potentially leading to the birth of new stars. These shock waves also distribute heavy elements such as iron, calcium, and nickel throughout the galaxy, contributing to the chemical evolution of the galaxy. Neutron star remnants continue to influence their surroundings long after the initial supernova explosion. The intense radiation and winds from young neutron stars can energize the surrounding material, creating complex and beautiful structures known as supernova remnants. These remnants, visible across the electromagnetic spectrum, are a mix of expanding gas, shock waves, and radiation, often exhibiting intricate filaments and loops. Comparing supernova remnants and neutron star remnants provides valuable insights into the aftermath of stellar explosions. Supernova remnants are the broader structures formed by the explosion's shock waves and the ejected material. These remnants can span tens of light years and are often observed in visible light, X-rays, and radio waves. The study of supernova remnants helps astronomers understand the energy and dynamics of the explosion, the distribution of heavy elements, and the interactions with the interstellar medium. Neutron star remnants, on the other hand, are the compact cores left behind by the explosion. These remnants, particularly pulsars, emit radiation across the electromagnetic spectrum, providing clues about the neutron star's properties and behavior. Observations of neutron star remnants allow scientists to probe the extreme conditions within neutron stars, such as their intense magnetic fields and rapid rotation. The combination of studying both the broad supernova remnants and the compact neutron star remnants offers a comprehensive view of the life cycle of massive stars and their impact on the galaxy. The role of neutron stars in supernovae also extends to their contribution to cosmic phenomena such as gamma-ray bursts. These bursts are the most energetic events in the universe and are thought to be associated with certain types of supernovae, particularly those involving the collapse of massive stars into black holes or neutron stars. The study of gamma-ray bursts linked to supernovae provides further insights into the extreme conditions and processes occurring during these catastrophic events. The impact of neutron star remnants on galaxy evolution is profound. By injecting energy and heavy elements into the interstellar medium, they help shape the structure and composition of galaxies. The shock waves from supernovae can trigger new star formation, influencing the birth and evolution of stars and planetary systems. The radiation and winds from neutron stars continue to affect their surroundings, contributing to the dynamic and ever-changing nature of the galaxy. In essence, neutron stars born from the ashes of massive stars in supernova explosions are both the remnants and architects of cosmic evolution. Historical discoveries. The study of neutron stars has a rich history, marked by groundbreaking discoveries and evolving theories that have deepened our understanding of these enigmatic objects. One of the most significant milestones in this journey was the discovery of pulsars by Jocelyn Bell Burnell, which opened a new chapter in astrophysics and set the stage for decades of exploration and discovery. In 1967, Jocelyn Bell Burnell, a graduate student at the University of Cambridge, was working with her advisor, Anthony Hewish, on a new type of radio telescope designed to observe quasars. During her observations, Bell Burnell noticed a series of regular repeating signals that she initially referred to as scruff. These signals, which appeared as sharp pulses of radio waves, were unlike anything seen before. After meticulous analysis and ruling out various terrestrial sources of interference, Bell Burnell and her team concluded that the signals were of cosmic origin. This discovery, initially termed as LGM-1 for Little Green Men, was later understood to be the emission from a rapidly rotating neutron star. These pulsars, as they were named, emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space, creating the appearance of pulsing signals when observed from Earth. The discovery of pulsars not only confirmed the existence of neutron stars, but also provided a powerful tool for studying these objects and testing the laws of physics under extreme conditions. Jocelyn Bell Burnell's discovery was a pivotal moment in astrophysics. It demonstrated that neutron stars, which had been a theoretical concept since the 1930s, were real objects that could be observed and studied. This finding led to a surge of interest and research into neutron stars and their properties. It also paved the way for the identification of many more pulsars, each offering unique insights into the behavior of matter under intense gravitational and magnetic fields. As our understanding of neutron stars evolved, so too did the theories surrounding them. Initially, neutron stars were thought to be relatively simple objects composed mostly of neutrons. However, as more pulsars were discovered and studied, it became clear that neutron stars were far more complex. The realization that neutron stars could have incredibly strong magnetic fields, leading to the discovery of magnetars, was one such evolution in theory. These magnetic fields, millions of times stronger than those on Earth, have profound effects on the neutron star's emissions.